In this example, we're going to discuss how to calculate 11 in 2's complement. So our goal is to get negative 11. The simplest way to be able to visualize this is figuring out how 11 minus 11 turns into 0 when we're doing binary logic. So this is how we have it set up. We have 11 in binary and 0 representing positive number. We have 1 and then some sort of values x where the result would be binary in order to get this result. So what's one way we can do this? The simplest way, let's initialize and what happens when we flip the bits. So we're going to do 0, 1, 0, 0. What ends up happening is if we add all these together, we get 1, 1, 1, 1, and 1. So we need some sort of carry in order to be able to wipe that all out and give us all zeros. The simplest way to do this is to have a carry in. So we have an initial carry in, and then we just do 1, 1, 0. It's going to be 0, and carry the 1. And we now see what we're trying to get. We're trying to get this cascade of values to deliberately get an overflow and get the 0 as the result. So we have 1, 1, 0. Carry 1, 1, 0, 1, that becomes 0 with a 1 carry, 1, 1, 0, that becomes 0 with a 1 carry, becomes 0, and then we have our overflow. But that's okay because we know, based off of what we determined in the reading, that if you have a positive and a negative number and you add them together, you cannot have an overflow where you lose information. 7 minus 6 is going to be 1. 6 plus negative 7 is negative 1. Those can be represented in a 4-bit representation, as we have here. So this means that we are having overflow by design. This is a good thing. Now, if you are going and reading on 2's complement, what it would tell you is flip all the bits and add 1. So in this case, we would take the 1, 0, 1, 1. We'd flip them all, 0, 1, 0, 0. And then we'd add 1, and that gives us 0, 1, 0, 1, and we have a sign bit. Why is this a potential issue? Let's say we have 1, 1, 0, 0, 1. Now let's say we flip it, 0, 0, 1, 1, 0, and then we get 1. So you get 0, 0, 1, 1, and 1. This works out well, but what happens if we have a 0 at the end here? Well, what's going to happen? Well, this becomes 1, 1, and then we add it, and now, watch what happens. We add 1 here to this, and we get 0, carry the 1, 0, carry the 1, 0, carry the 1, and 1. In more complex examples, what ends up happening is that students can make mistakes, especially if they're trying to do this on an exam. So they get some numbers, they have to erase it several times. It can get very confusing, especially under a time crunch or an evaluation. The other thing is that this is what the computer actually does. It flips the bit and uses a 1 as a carry-in. So as a result, this is a simpler way to do it and represented it on an exam and is more accurate with the way in which the computer does 2's complement. So flip the bits, have the 1 carry in, and then just add them up. And in class, we're actually going to see how that's physically done in a 4-bit full adder as we design it in class.